suppose this is our omega of eta, this function. Suppose our omega of eta looks like this, and our xi of eta, as I said, xi of eta, okay, if you put eta equal to 0, then you will get omega of eta is equal to xi of eta, that is xi and where is this? Okay, xi and eta have equal values. Xi of eta and omega of eta have equal values at eta equal to 0. Okay, this here it is. At eta equal to 0, xi of eta is equals to omega of eta. Okay, so and suppose our function omega of eta looks like this, and this is our xi of eta. Okay, so practically it means that our sufficient decrease condition of R-meso condition, it implies that our allowed values of eta are in this interval, here to here and from here to here, that is omega of eta is less than xi of eta. So this is our interval of allowed values for R-meso condition. Okay, this area, this region and this region. Okay, these are our allowed values of eta. And our second condition, that is curvature condition. This is our curvature condition. Suppose this is our gradient of omega at eta equal to 0, and beta 2 times this gradient is equal to this value. Okay, so if you since this value is negative, if you multiply it with some constant which is less than 1 and greater than 0, then you will get a higher value of it will decrease the magnitude of gradient, and since it is negative, so the gradient will increase. Okay, slope will increase. Okay, so it says that our allowed values of eta should lie in this interval. Okay, in this interval, and from here to here and from this value to this value, these are our allowed values. So if you combine both these conditions, this sufficient decrease condition and this curvature condition, then this our Wolff condition tells us that eta lies in the intersection of allowed values of eta lies in the intersection of two sets, that is set of values allowed for R-meso condition and set of values allowed for curvature condition. Take intersection of both these sets and you will get the value of eta. Okay, now this is our strong Wolff condition. Okay, strong Wolff condition implies that okay, I can choose value of beta 2. Okay, but the condition here is that it ensures that our eta should lie close to the minimizer. Okay, like here, this value, this is the value of, these are the allowed values of eta. Okay, let us focus on this interval in this region. Then it says that our allowed values of eta are from the in this region. So as you can easily see that our local minimizer, that omega of eta, minimizer of our function omega lies in this region, but the intersection of both these conditions will if we take intersection of both these sets, this region and this region, and this region and this region, it will give you the allowed values of eta from here to here. Okay, up to this value. But as you can easily see that from this value, our object, this omega of function omega again increases. Okay, so our strong Wolf condition take the mod on both sides, and it restrict this value of gradient to some to be less than equal to some positive value. Okay, so this is our strong Wolf condition. As you can easily see, if we in our Wolf condition, that is second condition of our Wolf condition, that is curvature condition, we choose values of eta from in this interval, okay, from here to here. And as I told you that our this is our local minimizer for function omega of eta, but as we can easily see, the curvature condition allows this interval and this interval. Okay, but if we restrict it to some if we restrict our eta, the sorry if we restrict our gradient of omega to be less than some positive value, then we can easily see that our eta is restricted in this interval for our curvature condition. Okay, and here it is restricted to this interval. So we can easily see that it forces our eta to lie near our local minimizer. Okay, as you can easily see, it forces our eta to lie near the local minimizer of function omega. Okay, so this is the practical meaning of a strong Wolf condition. And obviously take in strong Wolf condition, only our curvature condition is changed to this, and our R-meso condition is stay at it as it was in this Wolf condition. Okay, so this was all about Wolf condition, and this is very important condition for solving optimization problems. Okay, so now I make an assumption that there exists a set of values of eta for our descent direction q, such that they satisfy Wolf condition and strong Wolf condition. Making this assumption, I mean not an assumption, I will take it for granted. Okay, I will assume that our eta satisfy this set, and then I will derive necessary conditions, that what are the conditions necessary for this thing to happen. Okay, so let's start with this. Okay, I'm making an assumption that eta k, so there exists a value of is there exists a set of values of eta for which uh, strong Wolf conditions and Wolf conditions are satisfied, provided our q is our descent direction. Okay, so here I define that our this function is equals to omega of eta. Okay, and beta and beta 2 are as they were in the Wolf condition. Okay, so our R-meso condition was as it you can see here, this was our R-meso condition. Okay, now defining RHS in the R-meso condition as xi of eta, which is a linear function in eta. Okay, as I described earlier, and as I told that this function xi of eta is having negative slope. Okay, and we already proved that omega of eta and xi of eta intersect at value eta equal to 0. Okay, now as our q is our descent direction, and so our value of this our objective function should decrease in the direction of q. Okay, it cannot increase in this direction, since we are making sure that it is a descent direction. So it's obvious that our function omega of eta should decrease. Okay,